Hello everyone, it's been a while since I posted a video, but this gave me the time to think of how to organize content for this channel, and I believe that a more hands-on approach would be much more interesting than just going over some fancy features provided by whatever Python library I would like to cover. To this end, I would like to start with something that many of you may be acquainted with, that is to say the linear regression algorithm, which is a supervised learning method. If you don't know what supervised learning is, I will give a high-level idea of what it is so that you will understand what we are trying to achieve. And of course, in order to keep up with this video, you will need a little bit of linear algebra and some calculus. Nothing heavy, and bear with me. This is just the math on which we will build upon for the content coming in the next video, and you will see that many of the intricacies that are presented here will get much more easier for the next video. So to get started with linear regression, or I would say supervised learning in general, the thing is that we always try to find a mapping between some input x and an output y. In our case, our input x will be a d-dimensional vector. When I say d, that is to say that that vector has many components. You can think of it like the age, the height, the weights, and so on. Whatever you can think of. As many information you are trying to fit into that vector, the bigger the d grows. That's the whole concept. And when you batch, or let's say when you stack such vectors, you obtain like the matrix notation that becomes like an n times d matrix, and to say that we have n entries and all of them have d components in their vectors. That's why here you have like a capital letter X, and this one is lowercase, just to make a difference between the vector and the matrix. And of course, as I said, the whole purpose of supervised learning is to be able to find a mapping between X, our inputs, and Y, our outputs. And this mapping is our model. You can think of it as a function like f of x equal y. So the whole goal will be how to define this f, what it is. As I said, this is our model, and this is what we will try to build. So linear regression is defined as follows. You have two parameters in your model. The model, you'll have the model weights and the bias. The weights are a d-dimensional vector. Meanwhile, the bias is just a real scalar. Having defined our model parameters, now we have to see how to use it for inference. We have two cases. For the first one, we have a single input that would lead obviously to a single output. And to compute it, we just compute the vector products between the weights and the input x, and we add in the bias, which is just a scalar. And when you have a batch of these x input vectors, we use now the matrix notation. As you can see, this is a capital letter X and this is capital letter Y. But if you pay attention, or let's say look closely, you'll notice that this is not like just Y, but it is Y hat. We put the hats on top of it because this is a prediction, not the real ground truth. It's not 100% exactly what we are aiming for, because the model can make some errors, and it's based on these errors that we will adjust it so that we'll have more accurate predictions in the upcoming steps. But how to tell the model how far it is? This is where now the loss function comes into play. When dealing with linear regression, most of the time the loss function that you would see used commonly is the mean squared error loss. This loss consists of just computing the difference between the real ground truth and the model prediction, and then you square everything. The reason why we square it is to get rid of the negative signs, because randomly you may end up with something with a sum that's equals 0 here. But if you have only positive values, so implicitly you won't end up with 0, because if this whole loss function is equal to 0, that is to say that you have a perfect model that is accurate to 100% of the time. So That's the whole point. We would like to minimize this loss. So it's defined as follows. And based on this loss, and we have, let's say, this notion of error to know how off we are from the real ground truth. This is where now what we call the stochastic gradient descent come into play. The stochastic gradient descent algorithm is the updates rule used to reach the optimal values of our model parameters, and it is defined as this small difference operation. So here the theta parameter in the equation represents our original parameter. It can be the weight or the bias, and this fraction here is the partial derivative of the loss with respect to the parameter theta. So you can have the partial derivative of the loss with respect to the weight vector or the bias scalar, but we need both in our case. And when you have these two, what you can now use is what we call here the learning rate, the eta here, and the learning rate indicates the speed, or let's say the rates at which these weights are updated. The reason why we need it is because we need to take small baby steps towards the optimal values that will help the model have more and more accurate predictions. That's why most of the time you would prefer using a smaller learning rate rather than a big one, because if you take the big one, you may overshoot the optimal value. But if you have a small one, so it will progressively move toward these optimal parameters, but the model will need more time to converge this time. So it's a trade-off, and you have to play with it in order to have the right, let's say, the right dynamics when training your model. And the analytical gradients of our parameters are defined as follows. So you can just try to compute it yourself for those who are familiar with partial derivatives, but don't worry, when working with JAX, you won't need to dive this much and write this yourself. Everything is built in the library, and you can just use the gradients out of the box. JAX will compute them for you, and that's it. It will ease a lot of your machine learning pipelines. Having all of that said, this is what awaits us in the next video. As I told you, you won't have or you won't need to derive these gradients yourself. You can just use the jax.grad function that will return you a function that computes these gradients automatically for you. This is what we call automatic differentiation. And of course, we will build our own update function. This function will take in the model parameters, its gradients, and then update these parameters for us. And you will see that as we keep training the model, its predictions will get more and more accurate, and its loss will get lower, meaning that this model is learning. So see you in the next video.